Hello, I'm Katie Steckles.
And I'm Peter Rowlett. Hi Katie, what's today's mathematical object?
Today's mathematical object is an object.
Good.
And this is maybe a slight departure from my usual thing, but it's quite a meta one. So the object is an object, but obviously I know nothing about this, so I have brought along a special guest to help me explain what we mean by this. So welcome, Tai-Danae Bradley.
Thanks for having me, Katie and Peter. It's nice to be on your podcast. And I love the object that you brought today.
Yeah, well, it's great, isn't it? I mean, it's an object. So could you tell us what is an object?
So this is a great question. And since this is a math podcast, I think it's safe to assume that you don't necessarily mean the Oxford Dictionary definition of an object. So I think one way to kind of introduce this idea, I was actually thinking about the picture that usually goes with the objects on your podcast, right? Like either one of you has a picture or a guest brings in a picture. And if today's topic is object, maybe a possible picture for this episode could just be a collage of all of the other objects. Maybe that's what one might think. But actually, through the lens of category theory, which is what really formalizes the discussion of objects, that wouldn't quite work. And so I think it's helpful in describing what an object is to think about why can't we just consider the collage or collection of all objects that have already appeared on this podcast. So I claim that that doesn't work and that doesn't quite fit. So maybe one way to think of it is like this. In category theory, this is a branch of math that really helps you organize your mathematical thinking, and it kind of makes sure that everyone is having the same conversation. So if someone is talking about an object that has certain structures and, special properties to it, that's like a language, right? Like there's like an algebraic way of thinking, or you're speaking with algebraic language. But someone else may be looking at mathematical objects that are more geometric or topological in flavor, and it's like a totally different language. And so when you speak to one another, you kind of want to say, wait, if we're going to have a mathematical conversation, let's at least make sure we're on the same page first. Like, what kind of objects are we talking about? Are we talking about mugs, or are we talking about Rubik's Cubes? And actually, are those things related? So that's kind of where this idea of an object comes in more formally. You're kind of saying, okay, what do all of the objects have in common? And can we just talk about the collection of those objects that have something in common? So at least we're speaking the same language.
Yeah, I've heard category theory described as the mathematics of mathematics.
Yes,
which is sort of, again quite a meta thing, but it's this idea that you're looking at the structures that exist and saying what are the commonalities between them, I guess.
Yes, absolutely. So I think a good example, I think I mentioned Rubik's Cube. I think you had Rubik's Cube as an object on the podcast in a previous season, if I'm not mistaken.
Gosh, a long time ago, yeah.
Yeah, so yeah. That makes us think of groups. And so consider for a moment the collection of all groups. I don't want to say the set of all groups because that leads to trouble. So I don't want to get us in trouble, but just like collection with air quotes of all groups. And this kind of, aside from getting in trouble, it feels like a set. You just put a whole bunch of stuff together and you're like, okay, so what's the difference between that and like the collage of all objects on this podcast? So category theory is a little bit more than that, because you're not just interested in mathematical groups, all of the groups that you could think of. Those are like objects, examples of objects, but you're interested in the relationships between them. So here, like, how do you get from one group to another? So here's an example that I like to think about. Just think about the real numbers with addition. So here's some nice algebraic structure. You can add two real numbers and get another real number. They have additive inverses. You have 0, which acts like an identity. So that's a nice group. So if you live in group theory land, you're like an algebraically minded person, and you want to know, how do the real numbers as a group relate to other groups? Like, how can I look at functions out of the real numbers? So if you're a sensible person and you have this, additive structure and you're looking at functions on the real numbers, you'd like functions that don't destroy the structure you're interested in, right? Like you want functions that respect or are compatible with the addition. So here's an example. Take a real number and consider the function that just adds 1 to it. So take a real number x and consider the function that sends it to x plus 1. So now you can ask, does this function respect or play nicely with addition of 2 real numbers? So I have a real number x plus y. Either I can add x and y first to get x plus y, and then add 1. That's the function. Or I can take x individually, add 1 to it, y individually, add 1 to that, and then add the results. And you can ask, are those 2 things the same?
Yeah, well, initially my instinct was, yeah, sure, that'll be fine. But now that you've described that, I'm like, oh, no, wait, that doesn't work.
It's not fine.
Yeah.
Exactly. So this is like a super simple function, like just add 1, and yet it doesn't play nicely with addition of real numbers in the sense that, x plus y and then add 1 is not the same as adding 1 individually and then summing the result.
Yeah, you can't kind of swap the order in which you're doing those 2 things.
Exactly. So if you are an algebraically minded person, you live in group theory land, you have this group of real numbers, and you want to consider relationships or functions that play nicely with that structure, you've got to toss that function out. Like this is not something you want to work with. And so that's where category theory comes in. It says, okay, you've got a whole bunch of objects that you're interested in. And if you stop there, that's kind of like just working with a set, like the collage of pictures that we were talking about. So that's not what category theory is. It takes it a step further. You also look at how your objects are related to one another, where a relationship is like something that preserves or interacts nicely with whatever that structure is that you're working with. And so that's like these are group homomorphisms. So that's why in group theory, you don't just study all functions on groups, you study those that interact nicely with the group operation or group homomorphisms. So that's kind of like one way that I like to think of objects. They're things that have something in common, but the sort of special sauce of category theory is this emphasis on relationships between them too.
Yeah, I've kind of heard it described as like objects and arrows.
Yes.
And like arrow is just like, it's the most versatile thing in maths because you use arrows to like describe how a function maps something or like a relationship between 2 things or, from a, domain to another place or, we use arrows for so many different things. And I love that as an idea that it's like, it's not just the objects, but it's also the kind of relationships between them. And that's kind of an arrow.
Exactly. Yeah. And there's a little bit more to it because one might say, well, I can think of another branch of math that studies like things and arrows, graph theory, right? In a sense. So like, what's the difference between category theory and graph theory then, if we're thinking visually? So there's a little bit of extra structure, speaking of structure. So this is something that we all learn in, year 1 when we take group theory as a math major. But if you take 2 group homomorphisms, you can compose, if they're composable, if I have a homomorphism F and another one G and I can compose them, you can prove, this is like, homework on day 1, that F composed with G is also a group homomorphism. It also respects the structure. So this is nice because, just like you can add 2 real numbers and get another real number, you can take 2 morphisms in a category or 2 arrows in a category, sometimes called morphisms, and compose them and get another arrow or morphism in the category. So it's almost like the arrows themselves have algebraic structure, which I put in scare quotes, but it's really categorical structure. And so that's called compositionality. So to be a category, you need these things that they call objects with arrows between them, as you were saying, Katie. But then also, they're just not like arbitrary willy-nilly arrows. Like you can't just go draw a whole bunch of arrows and say you have a category. You also have to check that, hey, if I compose 2 of them, does this also give me something that respects the structure of the objects that I'm interested in? So there's a little bit more to it, but yeah, objects and arrows is a very helpful visual way to think about it.
Yeah, and I guess like, as you're saying, you can sort of apply this to lots of different things, right? So you can think about groups or you can think about functions, or you can think about like, I mean, I know you're saying it's not quite a graph, but can you do it with graphs? Like, can you have graphs that map to other graphs, or
yeah,
like,
so you can start with a graph and then get a category from it, because you might have a graph and maybe it has like 2 arrows, but maybe their composite is not in the graph. So if you kind of toss that in, so you can start with a graph and build your way to a category. So they're definitely related.
Yeah. But like, could you have a graph as one of the objects and have a map between graphs, or like?
Absolutely, yes. There's the category of all graphs and graph homomorphisms.
Yeah.
Exactly. Yes, the things that we know and love as mathematicians fit very nicely into this framework of category theory. So there's like the category of sets and functions between them, the category of groups and group homomorphisms. Like you're saying, the category of graphs and graph homomorphisms, category of topological spaces and continuous functions. The list kind of goes on and on. So there's many, many examples that people know and love.
Yeah, and that's sort of interesting to me that if you're going to study category theory, you kind of need to have an understanding of all of those other things, like in order to get how it works, maybe.
Yeah, so I will tell you the first time, well, I'll say, I first heard of category theory when I was an undergrad, and I just thought, and I actually heard it in the context of physics, like quantum field theories or something. What do I know as an undergrad about quantum field theories? Nothing. But I was like, oh, I don't know what that means. And I also don't know what category theory means, but it sounds cool. Then I went to graduate school. And I'll just admit, the first time I was formally introduced to category theory in a lecture, I thought it was the most boring, convoluted thing possible, because there's all these super abstract notions. Like, what do you mean a collection of objects? Like, like, are these bananas? How am I supposed to think of this? And the book didn't say, right? It's just definitions, like super dry. But it wasn't until I took more and more classes and then got an intuition, like a mathematical intuition for how things interact. The more math you do, the more you see like, oh, the people in this field are just doing what the people in this field are doing, but with different words. So you start to see patterns and phenomena reappear and reappear and reappear. And then when you have exactly what you're saying, that sort of breadth, and then you put category theory on top of that, you can kind of see, oh yeah, all of those examples and all of those different fields of math are all like instantiations of one concept that goes by this name in category theory. And so it's kind of hard to have an appreciation for the abstraction, at least in my personal experience, until exactly what you're saying. You're comfortable with all of these different ideas in math so that you can later see how they're sort of unified under this mathematics of mathematics called category theory.
And then, so what this is slightly reminding me of is sometimes people will, like, I have a bit in a talk that I give in schools where I talk about different things that are really graphs. So I have a chemistry molecule, and I have a delivery route, and I have a social network, and I say, haha, it's all really a graph. And if you know the graph, you can then learn things about all these different things. And is it something like that? Are we sort of doing, why are we doing this?
Yeah, exactly. So who cares about this stuff? It is a little bit like that, where you're taking things that people are already familiar with and then saying, oh, that's just an example of this other mathematical notion. In the case of your class, maybe it's graphs. In other cases, maybe it's category theory. Why is that helpful? So I think, like, why is this helpful? Who cares about this? I think it's safe to say some mathematicians care. In particular, a really beautiful place to be in mathematics is at the intersection of two fields. So just think about algebraic topology, for example. You could be an algebraist, you could be a topologist, but really interesting math comes when you kind of blend these two tools together. And that's actually where category theory was born. Back in the 1940s, was born in the sort of interplay between algebra, group theory, and topological spaces. And it turns out that if you want to study a topological space, it's easier to associate to it some group, like homology or fundamental group or something, study the algebra, and then send it back. So you kind of want to bridge between two different, I don't want to say islands because everything in math is connected, but two different realms of the mathematical landscape. So if you want to transport ideas from one branch of math to another, that's when this really becomes in handy. Like think about algebraic geometry too. Yeah.
I imagine there's like a moment when, like, if you're looking at these topological things and you're like, oh, well, there's this structure we can associate with this because of how it behaves. You know, this consistently is associated with this one and this is this one. But these are just those things that we already know about. And like finding that these are all already existing things must be incredibly exciting to sort of, I mean, my PhD was in topology and dynamical systems, which are two like not particularly related areas of maths, but we were looking at like the structures that you get in the orbits of objects and that kind of thing. Objects are back again, but like everything's an object, it turns out. But, you know, like looking at the interplay between those two things. And actually there's so much to sort of bring in from both sides that like you see something or you see a structure or a shape and you're like, oh, it's just that thing. We know what that is. And then you can go and grab all the bits of maths from that and all the things that people have already learned about that thing and then apply it to this new thing.
Exactly right. And, you know, you may say, well, maybe you could transport back and forth without knowing language of category theory. Like if you know the specifics of your discipline, do you also need to take a course in category theory to go back and forth? Maybe not. But if you have those kind of abstract tools at your disposal, that really equips you to see connections between other fields. You're like, oh yeah, I've been doing this already. I know that there's a word for this kind of bridge. Like we talked about categories, but this sort of bridge going back and forth is called a functor. So you may say, oh, well, can I find other functors in the wild? You know, or like, oh, my colleague down the hall is doing something similar. Oh, hey, that's just an example of a functor between two other categories. And now you can have conversations and you can talk about mathematical structures in a common language that maybe you weren't able to do in your domain-specific areas, because it's almost like, oh, you're speaking French and I'm speaking Mandarin. Let's just now speak in English so that we can be on the same page, that kind of thing, where English is like category theory, I guess. So that's one thing why people might care about it. But you know, so in the past few years, there's kind of a subdiscipline of category theory called applied category theory. And there's even a conference that's been taking place annually since, I want to say 2017, I think. I haven't been in a while, so I might be totally out of date with like the hot button topics in applied category theory. But the point there is that people are naturally finding ways to think category theoretically outside of the traditional mathematical objects. Today we were kind of talking about things that we're familiar with maybe from school, but the definition of a category is broad enough that there may be other things that you may find in data science or computer science or systems biology. I mentioned physics earlier. And as long as your collection of things have some notion of relationship, which you can define, and maybe it's like a social network, like maybe the people are, the things are people and arrows are like, you know, had lunch with or something. But then you'd have to check, does that satisfy the axioms of a category? And if you're lucky enough that you work in some domain outside of math and the stuff you're interested in does satisfy those axioms when you look at the formal definition, you have yourself a category. And now you can ask, can this mathematical way of thinking help me organize my thoughts in this other domain outside of math? And so there are folks that are really seriously considering that and working on that. I've done some of my own researches in category theory, sort of helping think about things in machine learning, and some things related to physics. And so it's just a nice way of thinking. It's really clarifying, I think. I like it anyway.
Yeah, well, this is one of my favourite tricks that maths does, is that like you look at something new that you've not examined properly before and you open it up and you look inside and you're like, oh, it's just that. And, you know, and you've got the tools there already. And I feel like this is like a really high powered version of that like you're coming in, you know, using this sort of very, a bit meta, but kind of quite broad approach that will fit onto so many different things. But it's the thing. So Peter wrote an article about this, about the unreasonable effectiveness of maths, that like, you know, there are lots of places where maths has suddenly become useful that we weren't expecting it to. And like, this sort of feels like that, I guess, in some way, that like there are now applications of this, even though it feels like possibly the most pure possible maths you could imagine, right?
That's a great point. And to me, that just speaks of the beauty of mathematics. I mean, you have all these mathematical ideas discovered independently. Then you do see like the connection to the natural world, which I think was, the sort of one of the points in the original paper, the unreasonable effectiveness of math. But then to see kind of the unification of all of those ideas in a single language, which itself is mathematics, is just delightful. I think it's great.
Cool, thank you. That was really interesting. So if people are interested in you and want to find you online, find out what you're doing, where can they do that?
Yeah, so folks can find me online. I have a website or a blog called Mathema. So it's just mathema.com, but it's spelled weird. It's MATH3MA, mathema.com. Also, I'm on Twitter too, and my Twitter handle is also Mathema. So yeah, if folks have questions or want to reach out, you can find me there.
Brilliant. And me and Peter are also both on Twitter and on Mathstodon. So I am at Stex.
And I'm Peter Ollett. If you want to get in touch or find out what Katie and I are up to, a great way to do that is through a Patreon called Finite Group. If you go to patreon.com/finite group.
There you will find what we've been doing lately, and you can also join us. And in fact, some of the episodes of the podcast in this series have been recorded in our Finite Group Discord, so people have been able to listen in. So you could do that. And also, Peter and I both blog at a website called aperiodical.com, which is where you can also find more episodes of this podcast.
And finally, if you have any thoughts or suggestions, you can email them to us, objects@aperiodical.com. The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.